and welcome back to this lecture. So we'll go into atmospheric compensation today. So it's just coming back to your exercises in the last 2 weeks. You had been working on gas retrieval and aerosol retrieval and how to apply this roughly to imagery or how to retrieve these parameters from imagery. And one of your tasks was to define a scheme how to correct imagery based on this knowledge. So it was maybe a very simple scheme, and it would be that you first retrieve the water vapor, then retrieve the aerosols, and then you'd remove the absorptions by the water vapor from the water vapor content and from the transmittance curves. And secondly, you remove the effect of scattering based on the aerosol content, removing the atmospheric path radiance, and at the same time taking into account the scattering coefficient of the aerosols. So this would be a rough scheme if you have only these two parameters. Moreover, what's missing is geometric influences. So you'd also have to think about how to include a digital elevation model or how to include the solar position and all that. So this would be additional points to the atmospheric parameters considered. So this is roughly the conclusion what we're going to do today. So we'll compile all these things into one scheme for atmospheric correction or atmospheric compensation. So first I'll talk a little about empirical corrections, and secondly about radiative transfer code atmospheric compensation. So sometimes it's also called physical and empirical, but I'll come back to that. I don't like the term physical in this context. And I'll go into implementation of that. We'll focus on the ATCOR model, come back to that later. And after having done such atmospheric compensations or reflectance retrievals, one needs some post-processing. So I'll go shortly into that as well. So how to polish your spectra, get nice spectra from your imagery, and how to apply possibly some BRDF correction. So that's about the content. So you should know about the goals, or what do we want to get, and being able to distinguish between the various approaches. And finally, in the exercises, you should be able to apply an empirical or a physical compensation routine, and knowing about the various steps involved in this process. First, about the goal. That's something which may sound easy. And what is the goal of atmospheric correction? And one could maybe think about that. Well, we have that situation, sun again, and we have LS at sensor radians. That's what we had looked into last time. And down here we have something, some reflectance on the ground. And the simple goal is to go from at sensor radiance to reflectance. So we want to have a reflectance retrieval, and this reflectance retrieval is, let's draw this nicer, LS, that's up here. So this reflectance retrieval is a conversion between a radiance quantity and a reflectance quantity, which is given as a percentage in the end. This reflectance quantity, the definition of that one, is already a question which is scientifically not easy to answer. So if you do the correction from, in this situation, we get a retrieval from at sensor radiance to a directional reflectance. So if you look at the situation, that's for sure a directional situation. So we don't have a unique reflectance on the ground after the correction, but we have a directional quantity which needs to be further discussed and analyzed to get a single value on the ground. So what types of reflectance retrieval do we have? Sometimes it's called physical and empirical. I mentioned this before. So if you're thinking about physical retrieval, this means we are making use of calibrated imagery. Calibrated means at sensor radians. So at sensor radians. That's in watts per square meter, steradian nanometer. That's a typical calibrated value we have. And if you have it calibrated, then we can compare it to the physical radiative transfer codes, RTCs, like Motran, 6S, Libertran. I introduced these last time. If it wasn't calibrated, there is no way to compare it to a physical model, and that's why this is both required to do a physical correction. That's also why it's called a physical correction. And then on the other hand, there are the so-called empirical methods, and those are using empirical knowledge about the properties of the object. So one has some knowledge, or one assumes for certain targets, for instance, that we know the reflectance on the ground, and then one can adjust the calibration. So this is empirical knowledge is used for kind of image-based calibration, or it's also called vicarious calibration, this term. I don't know if you heard that before, vicarious calibration. And this vicarious calibration is what you do, in fact, if you take some knowledge from the image and you relate it to your imagery, then you calibrate your imagery based on the image itself, instead of taking it to the laboratory. And then you can do a correction if an empirical model or whatever model you want. And this approach is not non-physical. So it's just you take some additional knowledge to adjust your imagery to a physical model. So that's why the term physical, I don't like it very much, because both of them are some physics behind, but it's different kind of approaching the physics behind. So I'd say here that's RTC based correction, and this is target based, or in nowadays it's usually if they fly a drone, they put up a white panel and they use this target as a calibration base for the drone imagery and for the low altitude imagery. Then about the terms, I can also maybe have a little explanation. There are various terms for these kind of corrections. So for instance, you got atmospheric correction. We also got atmospheric compensation. Both are used. Historically, the process has been called atmospheric correction. The correction term, if you use that one, it implies that something was wrong, and that's not what we. Oh, I lost it. So that's not what we wanted. So nothing is wrong with our imagery. That's why the term atmospheric compensation is the better one. We compensate for the influences of the atmosphere, and even there, I think it's not a better term, because you don't only correct for the atmosphere, you also correct for the geometry and for everything else what's happening radiometrically in the imagery. So nowadays, one rather uses the term reflectance retrieval. That it's just coming up the last years. No, it's deep already. So it's reflectance retrieval. Why that? It's coming from drone imagery as well. So they use the panels and just said, I want to have a reflectance. However I get it, I just correct with the panel, and then I do a retrieval of my reflectance. And I also like it a little bit better, because the goal of the whole process is to get some reflectance. That's it. However you get it. if it's a good reflectance in the end, you did a good correction or you did a good atmospheric compensation, or if it's physical or you have empirical elements in it. That's just an academic question. That's not a question in practice. In practice, what you want is a reflectance fitting to any other measurements of the same target. That's the goal. That's why reflectance retrieval, I'd say in the future, maybe I rename this part of the lecture to reflectance retrieval instead of atmospheric correction. So that's so much about the terms. Now about the empirical approaches. Empirical approaches, I don't know if some of you may already have done this empirical line correction. I come now to the theory behind that. The empirical line relies on a simple assumption that you got the sensor radiance here, which is related to the reflectance times a constant plus L atom, the atmospheric path scattered radiance, single scattered radiance, so the portion of the radiance which never reached the ground. This model neglects the adjacency effects. I mentioned them last time, but it has a simple linear relation between the reflectance and the sensor radiance. So you can summarize all these effects by C rad and as a constant to the reflectance plus an additive component. So this is a linear thing, linear between reflectance and the sensor radiance. It's mostly linear. Maybe you know about as long as it's linear, as long as the sensor responds linearly to radiance. So with linear sensors. And from sensor theory, you may know that at some point the sensor starts to saturate, it won't get more photons registered, and so linearity is not always fulfilled, specifically for bright targets. So if you analyze imagery in the end, you may see bright targets which look strange because they just didn't get the full radiance registered. And this, the same quantity can, the same equation, if it's calibrated, can also be used in non-calibrated state. So then you will have the digital numbers at sensor, DNS, so that's at sensor DN, which is related to the reflectance just by a calibration gain. Which is just telling us how much DNs we get per reflectance. This gain not only includes the terms above, it also includes possible calibration information from the sensor. The same applies to the additive dark current, DN dark, which includes now, if you apply it in that way, the atmospheric path scattered radiance, but also electron noise from the sensor, all additive components visible in the digital numbers you measure in a sensor. So this empirical approach can be done in a very empirical way with completely uncalibrated data. And you just search for a linear relation there. And don't care if it's coming from the sensor or if it's coming from the atmosphere. So that's the basics for all these empirical approaches. And there are a few possibilities to apply them. The most simple one is the flat field correction. This is also implemented in the Glimpse software. So what it does, it searches for a flat spectrum. So a flat spectrum, what does it mean? It searches for a spectrum which is with wavelength more or less like this. Flat means no absorptions in the spectrum. It's not about flat areas on the ground. It's not spatially flat, it's spectrally flat. And these flat spectra are affected by absorptions, of course, so they will have these small absorptions in there. And these absorptions can be measured now from this flat spectrum. So if you know, we know certain targets have this specific shape I've been drawing here. So like sand or asphalt, these kind of targets should be spectrally flat. And if you manage to find such spectra from the wavelengths which are not affected by the atmosphere, then you can assume that in between there should be straight lines. And all the difference to the straight line is an atmospheric effect. So you can just relate these, find the atmospheric effects from this difference and divide it into the original data. Then you can get a corrected imagery. That's a trick with this flat field spectrum. So you adjust the spectrum according to a flat spectrum. It's very simple. The only disadvantage of that one is that you'll have relative reflectances. So to a flat field, you don't know the absolute value of this one. This could be maybe 30 to 50% reflectance, but you don't know exactly where it is. So it's just a kind of a absorption removal approach. But it's very fast and very simple. Then the next one is the bright target approach. So you just assume in one wavelength that we get a 100%, maybe let's draw that one. We know where 100% is, and we may have a bright target spectrum somewhere. That's rho bright, and we know the d-ends of the bright target. So if we know the rho bright, if we know this reflectance, then we can divide by the d-ends of the rho bright and multiply with the d-ends of the real measurements. So the relation of the reflectance of the bright target to the d-ends of the bright targets gives us a calibration factor to get the reflectance itself of the pixel. That's rho s here. So that's you need to know the reflectance of the bright target. That's something you could also do with the empirical correction, with a single target, bright target correction. And if you know it's about 80% or 70%, you can do this correction quite easily. You could even feed a spectrum if you know, if talking about panels. So if you have a spectralon panel, maybe panel, these are about 99% reflecting targets you can put up in the field. And this, if you put up such a field spectralon panel, you can directly apply the bright target correction. That's what the drone guys really use. They just put up a spectralon panel with very high reflectance and normalize to that one. That's the bright target approach. So one single target, one target. Then the dark target approach, that's what you did in your exercises, more or less. Well, you only did the subtraction of the dark signal in your exercise. And if you'd not have it calibrated, you could even divide by the irradiance, the average irradiance, and that's how you'd get a reflectance as well. So it's dark target subtractions, or it's it's also called as DOS, dark object subtraction method. So dark object subtraction direction. This usually only does dn. The most simple way to do is just dn minus dn dark. So you find an average dark signal, you subtract it, and that's it. So this is the very most simple dark object subtraction method. And if you want to do a reflectance retrieval with that, you have to divide by some irradiance. So much about these simple ones. Those are, I guess, for you not of much relevance. It's maybe if you do a very fast and dirty correction, you can do it that way. But in general, it will not be applicable in quantitative remote sensing. So nowadays, one shouldn't do this, I'd say. That one is a different thing. It's the empirical line correction. So what do we have? We have a relation between the digital numbers and the reflectance here. And these are always, I said it's a linear relation. So that's rho of dn, this curve, and which relates the reflectance to the digital number measured at the sensor. If you got zero reflectance, you already get some signal. So this thing here is basically L atom plus calibration offset. That's this offset you see here. So even if it's completely zero reflectance, you get some signal. That's the point. Even if it's zero atmospheric influence, you'd get some signal at the sensor because you always have some calibration offset, some electron noise in the sensor, which gives you some signal, very small signal measured. So sometimes sensors are doing internal corrections and you get negative signals, but usually it's positive. And second thing is that you need to define the slope of the line. So that's delta rho over delta n dn. So this slope has to be found somewhere from, and this can be found by two targets, by rho. I think it will show it here. Yeah. So so you got rho 1 and rho 2, two targets, known reflectances, and you relate them to dn1 and dn2. So that's dn1 here. This one is dn2. And these two relations, or these two known targets, can be used to find a calibration curve for each spectral band. So what you need to do is to feed two targets, one dark one and bright one, and to feed the full spectrum of those and find them in the imagery, assign a region of interest, and then combine the two, and then you get a linear relation. So one catch of this method is that if you'd have the two targets, for instance, like that, say you got, that's the wavelength, that's my reflectance, and I get one target which is maybe a soil. A soil is typically looking like that, and then you got some vegetation. The vegetation is typically looking like that. Now, at any wavelength, we need two targets. For instance, here it's no problem. We have two targets, but where the two cross, at that point, it's not defined. You can't find a slope for the correction. So two targets should be completely distinct in brightness for the full spectrum. And because you may not find such combinations, you should maybe rely on three on three or more targets. So you search for another target, maybe down here. And then if you have all these targets together, you need multiple targets to do a linear fit. So you get a much better empirical line if you, for instance, have 3 or 4 targets in the image, known targets, and then you can do an empirical line correction, or you could even do empirical vicarious calibration. So if you have an uncalibrated instrument, a few targets in the imagery, and you have the atmospheric model behind, then you can do a full correction of all the instrument effects. So much about empirical line correction. Question about that? Don't see anything. There is another method which has been implemented in ENVI. It's called the quick atmospheric correction, the QAC. And it's a very nice idea. And what they say is, in certain areas of the world, or in certain climatologies, an average image looks always the same. The average, if you take the full image and take an average spectrum of the full image, this should have a certain shape or a certain brightness. That's their approach. So they put together kind of a database which tells you how an image in average should look like. And then so what they do, they calculate now from the image the average spectrum, and they search in their database a good fitting average spectrum of the reflectance. And now you can get a gain between your average in the scene and your average from the database. And this can be applied to this gain or this relation can then be applied to the digital at sensor radiances or digital numbers at sensor according to the equation to the right, to that one. And you see that's a very simple approach, and it's working surprisingly well for retrieval of relative reflectances. So it's not getting you to absolute reflectances, because this average is sometimes bright or sometimes less bright. So it often is not accurate enough for absolute reflectance retrieval. And it's also kind of a quick and dirty approach. People in the military like that one because they need fast results. For scientific applications, I wouldn't recommend using this approach, because it's just not an absolute value what you get. You get just something which is not really known. So much about empirical approaches. So what are the advantages? Why are you still doing that even though it's not accurate? Well, it's very fast. That's the major and big advantage of empirical approaches. If you once have a linear relation, you have in seconds you got an image corrected. And you don't need any calibration, so cheap instruments can be corrected right away. And also, you don't need to be an expert to apply them. You can do some qualitative image analysis based on those, such as target detection. So if you go into spectral unmixing or spectral matching algorithms where the brightness does not have an influence, so like a spectral angle mapper, you learned about that, I know. Then with empirical approaches, you can get quite nice results. If you are not trusting your instrument, that's the second thing. If calibration is bad, then sometimes I'd recommend going for empirical approaches. Disadvantage, you don't have adjacency included. That's terrain. So if you look at dark objects, it won't work. And you assume that everything is constant within the whole image, so no variations of the geometry and the atmosphere. And of course, you depend on the reference target reflections. So you're always not as accurate as your reflectances you get for your reference targets. And you would also say, and the BRDF of the reference targets. So if you measure in the field some reference targets, they are affected by BRDF effects, and this is roughly 10% accurate in reflectance. And so that's how you see how accurate you will be in the end with empirical approaches. You're never more accurate than in a range of about 10%. That's just the limitation of these approaches. Due to the BRDF being easily 10% off. Of course, by luck, you may be more accurate, but you cannot claim that you will be more accurate. So much about empirical approaches. How many targets do you need for empirical line correction? Questions to you, just think about these questions here. Exactly. Some are writing in the chat now. Number one. Why is the dark target approach difficult to apply to reflectance retrieval? Well, Any idea? We're talking about reflectance retrieval, not only about correction. So what dark target approach is like a correction for the diffuse radiance, and it will enhance your contrast, but it won't give you as a result a reflectance directly. So it only corrects some influences of the scattering. So that's number 2. And so here it would be more than 2. Sorry, I should have written more than 2. And why is it difficult to no reflectance retrieved? Only DOS, or only dark object subtraction is what is usually done. So this means a subtraction of the signal. And also why is the correction of aerosol effects insufficient with empirical approaches? Well, aerosol effects is just, that's the adjacency question, no adjacency. And aerosol effect, the adjacency effect is also easily 10% of the whole signal, specifically in the blue or red area of the spectrum, or the visible part of the spectrum. Is the measured signal of a system always depending linearly on the surface reflectance? One would assume that, but it's, if you got dn and the reflectance, it's usually, you got already some dn's here, but it's going up linearly, and at some point it starts to get saturating. So that's where the linearity is not given anymore. That's why if using empirical targets in the field, it's not recommended to use the 100% reflecting targets. Even though they're easy to apply and people are buying them, it's much better to use about the 40% or 50% reflecting target, which is in the range of what you'd expect as a signal as well in your imagery. And then you avoid the problem of running into saturations at certain wavelengths. So much about that. Now let's go into the radiative transfer-based atmospheric corrections. And you remember that one? I was talking about that one last time. And this is the radiative transfer components. And what's the how do we get this retrieval based on these radiative transfer components we have from the code? So what we need is a correction equation. So we invert what I was talking about last time, and maybe I'll put this together step by step instead of just showing it. Let's try it again on this side. So we start with, we want to have reflectance somewhere. And well, reflectance, talk about that afterwards. What it's a kind of hemispherical directional kinds of a hemispherical directional quantity, which is, but not the real HDRF, it's the measured HDRF. And what we have is the, wieso steigt da mal probieren wir es nochmal. Oh, HDRF. So we got the LS at sensor radiance. That's where we start. That's the measured, calibrated at sensor radiance, calibrated. And we have to subtract a few things. We have these additive components. So we have to subtract the adjacency effect, and we have to subtract the atmospheric radiance. So these are the additive components subtracted. Now we are still at top of atmosphere. So we are up there. We had these 3 components coming up, LLS, L adjacency, L atom, and we only want to have the one in the middle. And now we have the tau upward. No, it doesn't work that way. I'll do it on this side. And so we have the LS minus L adjacent minus L atom. And we have the upward path. Stupid stuff. Machen wir es da. So we have the upward path from the bottom up. We have the upward transmittance as well. We had these three components. Let's try it again. Adjacency minus L atom. And we have got to divide this 1 over tau upward to get rid of the upward transmittance. And so now we are on the ground, more or less, from the sensor position. On the ground, we had these irradiances. We had the EG somehow, and this adjacency, this irradiance on the ground was the addition. I did it last time already. Was the addition of the diffuse and the direct irradiance on the ground. So you had this E0 times cosine phi. This is the direct irradiance plus the diffuse irradiance, E diff, from the sky. And if you got some terrain, then you have to take into account the sky view factor, so that if diffuse sky irradiance, and moreover you got some terrain irradiance. A little bit too much here, and so E terrain. This makes these few effects, or this correction, almost done, but there is something missing in the end. That's the pi. If you go from radiance to irradiance, then HDRF. So then you have to multiply the upper one with pi as well. And you got to take the Sun-Earth distance into account. That's the d squared. So that's the thing missing. And that's already the whole game. So if you have all these parameters defined, then you can do an atmospheric correction or a reflectance retrieval in a physical way, or based on a radiative transfer code. So going back here you got the same again as the same equation again. I just wanted to derive it such that it's explained. And now how to get these parameters. If I'm going to next slide again, then we need to get these parameters somewhere from. And one can think about where you can find them. So there are, this one is measured. That's measured. Then what else do we have? We have the, some can be found from the radiative transfer code, like that one. So the atmospheric path radiance, the transmittances, there is one transmittance missing, tau downward. I forgot that one. That one can be measured in the radiative transfer code, and maybe E diff. So these are from radiative transfer. So they can be calculated with Motrin directly. Now there are still a few missing, and those, for instance, that one, and that one, they are from geometry. You know the geometry of your image, you know the sky view factor from the terrain, you know the irradiance angle, and you know the distance from the sun. That's geometric astronomical thing. So we got almost everything done, but we have a little bit of troubles. Well, E0 that's a constant, like the solar spectrum. and we have the adjacency missing, and maybe also the diffuse can, or the terrain, that one is missing. Those you don't know at first. You need to do an iteration. Iteration means you first, for the adjacency effect, you first do a correction, and then you get a guess of the reflectance of the surroundings. Then you put it back into the model and do a second calculation, and that's how you get the adjacency correct quantified. So that's kind of a mess on here, but as you see, we have three sources for the correction. We have the physical model, we have the iteration, and we have the boundary condition, the geometry, and the background. And of course, we have the sun, the astronomical, that's astronomical parameters. So these are the sources of the parameters, and then so we're well done. Now we can find everything for every pixel. So how is the setup now for the correction? Let's start over here. If a Motran, the radiative transfer code, you create at sensor radiances. That's what a radiative transfer code does. It does a forward. That's a forward simulation. Forward means in direction of the radiative path. The radiative transfer code Motran does not do a correction. It doesn't do an inversion by itself. So you need to be prepared for everything what can happen in a correction. So you put in an expected parameter range. For instance, you put in the expected aerosol amounts which could happen, the water vapor amounts which could happen, the geometric situations which could happen, and do all the simulations which could potentially happen in an image. And you create a big lookup table. Let's look up table, LUT. So this big lookup table contains everything which could happen potentially in an image. So with this part here, that's the RTC part, the forward simulation creating the lookup table. Now, if you go to the correction, you go the opposite way. That's a kind of an inversion of the model. So instead of doing a forward simulation, you invert the Motran model, and the inversion is done by other packages like the ATCOR code. So that's the atmospheric correction software which does this inversion. And what you need is the calibrated radiance. Here, going upwards, you get LS simulated, and here you get LS calibrated. So it's not necessarily the same, because calibration is not absolutely accurate, but it's close to each other. So we assume we have absolutely calibrated radiance at sensor. And then we go downwards to do the atmospheric correction. The atmospheric correction uses all the parameters stored in the lookup table. So it interacts with the lookup table and retrieves for each pixel. It retrieves the appropriate parameters. So each pixel has a different geometry and may potentially have a different water vapor amount or whatever. So this is retrieved, and the corresponding parameters are retrieved from the LUT. And then this thing is apply equation. So if you have all the parameters done, you can apply the equation I've been explaining before. Then you get kind of a reflectance on the ground. Of course, the geometry is going into here as well, because otherwise you couldn't do the retrieval of all the parameters. So that's pretty much explained what should be done in theory. And any question for now? I don't see any questions popping up here. You're so quiet. That's astonishing. So then we're gonna have a break for 15 minutes, and I'll continue with these corrections afterwards.
Danny, can you pause the recording for the break?
Yep.
Perfect.
Okay. So let's continue. So this was the process of correction, and the basic, the core part of the whole correction was this strange lookup table. And to explain what's in this lookup table, you store a few parameters. You store the transmittances, upward and downward. So that's the downward. It's downward. So this was in the text before, it was T upward, T downward. Diffuse irradiance, that's E diff. And then you had the direct irradiance, E 0 times tau downwards. It's usually stored that way. And then you have the spherical radiance, L ATM, and the spherical albedo S. These are the parameters which are stored. Each of them is related to geometry and wavelength, for instance. So each of them is not a constant by itself. So they have to be related on various parameters. And these are the so-called dimensions of the lookup table. We have the water vapor. This is usually called PW, like precipitable water, or sometimes also big little u, and it's given usually in centimeters. How much water you have in a column of in centimeters from through the whole atmosphere. Also sometimes in kilograms per square meter, that's the same, or in grams per square meter, then you get also a centimeter. Then the aerosols is usually given by visibility or AOT, aerosol optical thickness, or depth, AOD, for vertical atmosphere. Then you got the height of the sensor, H1, H2, and the ground. So you got the ground altitude and the flight altitude for airborne systems, wavelength, that's lambda. Then you got the reflectance, rho. For the reflectance, because it's a linear relation, we only need 2 points. Usually one stores the values for 0 reflectance and 30% reflectance. For the solar zenith angle, you get an azimuth angle, that's theta and phi. These are the 2 parameters. You need some kind of a raster, and usually this makes about 2. This makes about number of wavelengths. That's number of bands in your that's maybe 300. Then you get the heights. There we store about 6 to 8. Aerosols, it's also in the range of 6. Water vapor is in the range of about 7. And solar azimuth is about 8. So we store, or we calculate for 8 solar zenith angles all the other situations. Now you can do the math. You have 6 parameters on one hand side, and we have 1, 2, 3, 4, 6 or 7 dimensions. Each of the dimension, all of the combinations of the parameters in the dimensions have to be calculated. And this makes quite a lot of calculations. So it's 7 times 6 times 7 times 300 times 2 times 8. You can do the math yourself, but it's a few thousand calculations. And all of them need to be stored in the lookup table by 6 parameters. So the lookup table at first, if you do the first calculation, has a size of about 12 gigabyte. That's what you get if you have a higher spectral resolution. Of course, if you have less wavelengths and so on, then you can go down to a few, about 100 megabyte per sensor. That's at at 0.4 nanometer resolution. You get the original lookup table, and there are a lot of calculations involved. Radiative transfer is a complicated method. So the calculation of the lookup table, as we did it now, takes about a few weeks of calculation on a computer, and then we get the lookup table redone. So this is not calculated every day. Only if there are major changes in the radiative transfer code, we have to recalculate the lookup table. This takes a long time. And so, but this resampling to the sensor, so that from the 12 to 100 megabyte, that's done easier. In your exercise, this has already been done. So you start with the 100 megabyte situation. So you don't need to resample the lookup table anymore. But that's about lookup tables. Question? No. So now we have the lookup table. So you can do the correction. Here is as a text what you have to do. We have first lookup table calculated, and we create it specifically to our situation. Then we need the height and position of each pixel, sky view factor, and the angles, so the geometry is done first. And then some things have to be fixed. For instance, one assumes a constant flight altitude, so assuming the aircraft is not changing its altitude while taking the picture, which is normal. Or we assume a constant aerosol model like the rural aerosol model. Then some parameters have to be derived, like water vapor aerosol, maybe haze, and then the lookup table can be inverted. First, we need to derive the parameters for the 6 parameters for each pixel. Now, I said before that we have maybe only 5 calculations for water vapor, but we are somewhere in between. So it's a multilinear interpolation. For each parameters, we interpolate to the real value we are expecting in a pixel to get the 6 parameters right. So it's a 6-dimensional interpolation, which is done there. And now we have for each pixel all the 6 parameters, then we can apply the equation. Number 6 and 7 can be iterated to get the adjacency and terrain irradiance. So that's how it looks like as a correction, as a scheme. So we start with lookup table, topographic data, the sensor data, and the geometry. First one does a little pre-classification, because for the parameter retrieval, we need to know where the water is. We need to know where clouds are, such that we get correct results. So this is a pre-classification done on the raw imagery. And then you do the aerosol and water vapor detection. Also, the cirrus and haze removal is done in a first step, because cirrus and haze removal is done on the statistics of the data. You don't need the calibrated data for that. So you detect these two things, remove the haze, and now you can go into the atmospheric correction using, on one hand, the aerosol and water vapor data, and on the other hand, the terrain information. And now this was the iteration here. So this is the iteration to get the adjacency correction done. And so you get the second order atmospheric correction. And as an output, you get the irradiance for each pixel, and you get the bottom of atmosphere directional reflectance. So this directional thing, that's what you would measure on the ground instead of measuring from the sensor as a reflectance. So if you put up a spectrometer on the ground with the same directionality as the sensor, then you'd measure the same. That's the goal. That's the output of this procedure. Now this is not yet the full game, because what we want to have is spectral albedo. So the problem is you have this situation. So we have that's the bottom of atmosphere, BOA, bottom of atmosphere reflectance. I think that's the best term describing what you have after atmospheric correction, bottom of atmosphere reflectance, because you have a directional observation. So observation is directional, irradiance is non-uniform. It's the problem. The irradiance is, you got a directionality from the sun, but you also got the diffuse irradiance, which is completely non-uniform. You get a little bit more close to the sun. There is the terrain blocking some of it. So it's not well defined what you have as an irradiance. So that's why this is no real HDRF. It's maybe rho boa would be the best term for this, what you get after atmospheric correction. Now we want to go to the spectral albedo, and spectral albedo is, maybe you remember, is the relation between two bihemispherical reflectance. This means that's what you'd get if you illuminate with full white light from all directions and you measure the integral of all reflected radiance of the object. That's a spectral albedo. That's one value, one unique spectrum. That's the big advantage of spectral albedo. So one object has one spectrum and not various of them. So it's the best way to identify an object. Of course, you lose the information given by the directionality. So some objects have some information like vegetation, where you can use the directionality to get some biophysical parameters from it. So that's what you lose if you go for spectral albedo. On the other hand, if you only have one direction of measurements, it's very hard to make use of this directionality for parameter retrieval. Okay, so how to do that? This is already the BRDF correction, what I'm going into here, and I'll show this later again, but you need some BRDF model to get from the bottom of atmosphere reflectance to the spectral albedo. The BRDF model is the Ross-Fickley sparse model. It's the most often used, is RTLS. And then you calculate the so-called anisotropy for each pixel. So you calculate how much it deviates from a full BHR. And using this anisotropy factor, you can do the BRDF correction. I'll show some slides regarding that later. So that's why I don't explain it in more detail now. Let's go first to the bottom of atmosphere reflectance outputs. What do you get as a result? Here is a result of airborne data correction taken from about 1 kilometer above ground. And the dashed line is the spectrum before atmospheric correction, apparent reflectance before atmospheric correction, and the solid line is the one after. What you get corrected is the atmospheric absorption features, like that one, and they are more or less corrected, and you get some noise here, feature correction. So that's well done, more or less. And the noise is something I'll also go into later if you still got time. And the other thing which is correct is happening is in the blue. So the dark objects are corrected for the additive scattering effects, so they get darker, whereas brighter objects like the sand spectrum here is not affected by the atmospheric correction. So that's what I mentioned last time. Aerosol effects, they cancel at a certain brightness. So if you're at, here it was 5 to 10% reflectance, you hardly see an effect of the atmospheric correction. There's a little bit of an effect because I guess that one would have been down here originally if it was yeah, it's they're approaching each other a little bit, so it has been reduced a little bit by aerosol scattering. Don't know why it's what's happened here. Something I should have looked up. Yeah. range. Yeah, it's how to calculate the apparent reflectance is not as easy. I guess that's a calculation problem of the apparent reflectance. Because if the apparent reflectance, you take the at sensor irradiance instead of the ground irradiance, which is different, and that's why you don't get exactly the same reflectance level for apparent reflectance. So if you look at the spectra in the end, you may see shapes like that. And if you want to analyze if they have been well done, you maybe first look at the blue part. In the blue, usually spectra are getting darker. So that's what you'd expect, that they go down in the blue. Almost all objects are getting dark towards blue spectral wavelengths, and they shouldn't go below 0. So if you get sometimes you have overcorrections and you get 0 or less reflectance, of course that's physical nonsense. Then we have a look at the 500 nanometer range, and if there are lots of variations in there, maybe you have a problem with the solar spectrum. I mentioned these Fraunhofer lines. If you're having a sensor with 2 nanometer resolution, this may cause artifacts in this wavelength range. Then the red edge is to be analyzed. Red edge is analyzed at first. Of course, you will see it in all vegetation. If you analyze at the same time non-vegetation areas, you shouldn't see the red edge. So if you analyze a clean water or an asphalt, it should be a straight line like the brown line below. If you still see a red edge, well, what could it be? It may be the adjacency effects not corrected correctly. If adjacency is there, you have a lot of vegetation, and you don't correct for the adjacency, you will see vegetation signatures over asphalt. And this is wrong. So the correction was not done well. Then we have the green oxygen part. Oxygen is a very sharp absorption feature, and if you still see a lot of variations there, you have a problem with the spectral calibration. And then the water vapor should be corrected more or less, and this should be more or less straight there, or a continuous line. That can be analyzed as well. Then the spectral range. So that's maybe the most important one. So you should have a little bit of experience for that, but normally you shouldn't get more than 60% reflectance anyhow. So the natural objects are never very brighter than about 60%. Vegetation shouldn't go about 50% more, not more than about 50% reflectance in the near infrared. Maybe some football fields or so will be brighter. If it's very bright grass, it may be 60%, but usually it's between 30 and 50. Here it's even less. It's maybe darker vegetation or affected by illumination problems, then it's usually darker. And the same in the visible, you'd expect reflectance is below 10%, as you see in this slide as well. Now, as you have seen, there are a lot of small spectral variations left after correction. And where could they come from? Well, first, I talked about the solar spectrum, and there's also the underlying RTC model. These are both not absolutely accurate, so you can get problems there, but nowadays we use the latest technology, and it shouldn't be a problem in the level of about 5 nanometer resolution. If you're at 1 or 2 nanometer resolution of instruments, then we get a problem there. So we still see these wriggles and little variations. Ozone may be a problem as well. It's been solved for satellite imagers in the meantime, and spectral calibration. So you need often to recalibrate your system, higher resolution systems, and then you can get rid of most of that. And if you still see these variations, because you know it's not natural, so naturally you'd get variations in a range of 10 or 20 nanometers, so you can apply the spectral polishing. So So much about the theory. I'll go into implementation afterwards. What's the major term? The correct term or the best term for the atmospheric compensation output? Yeah. And I'd say it's the, remember first I introduced HDRF, and some people are using the term HDRF. I rather like BOA, bottom of atmosphere reflectance. That's and it's a reflectance and not a reflectance factor, because you relate an incoming radiation to an outcoming radiation. You don't measure over a target. Which parameters are we get iteratively? Well, that's L adjacency. There's another one. No answer so far. Nobody dares to answer. Yeah, the terrain irradiance, thank you. Then we got the next one, name of the dimension of an atmospheric lookup table. What are these dimensions used for? The dimensions, the name, well, all the 6 of them, I don't, they are, the major dimension are geometry, atmosphere, and wavelength. These are in the generic dimensions. For the atmosphere, we got about 3. For the geometry, we also got about 3, and the wavelength is an additional 1. And what are the dimensions used for? Well, if you want to find, they're used for pixel-wise correction. So you go for in each pixel and search for the geometry, the atmospheric state, and the wavelength, and then you apply this. You search in the lookup table the correct value based on these dimensions. So the loop by or from lookup table. Assumptions. Most important, what we do is clear sky. I never mentioned this now, that's why I don't wait. Clear sky conditions and calibrated instrument. Clear sky conditions, it's almost impossible to model, to put together a lookup table for all cloud situations which potentially could occur. That's why one assumes that the data has been taken under clear skies. Cloud shadows and so on are a big topic, and nobody has a good solution to them yet. Any questions regarding the theory? No further question? If not, then let's go into implementation. And I go through the atmospheric correction software setup. So what if you want to do a atmospheric correction, you need all that I have been explaining before, like a lookup table, you need these parameter retrievals, you need to know about VRDF, topographic influences, and so on. I don't go through the full list because I have been explaining this before. And now what software packages are available? There are not as many atmospheric compensation softwares. And there is, on one hand, is the Flash module. That's an add-on to Envy. That's a complete solution for flat ground. And the Quack I mentioned before. And on the other hand, there's the whole ATCOR family, and that's the one we are developing ourselves. And it's it has become one of the standard procedures for many satellite providers and airborne data providers as well. And that's why I think it's good that we rely on that one. We have two of them for airborne and spaceborne, and there are implementations in PCI and also in ERDAS of the ATCOR model. So they once bought a license from DLR when ATCOR was still with DLR. So these are the 4 ATCOR models. Below, these are to be announced. So these are 2 models which are currently developed. I'm just these days I'm developing on these models because there is no atmospheric correction software, physical-based atmospheric correction software available yet for drone imagery. So if you fly at low altitudes, people are still using the empirical approaches for reflectance retrieval. And in some situations, it would be nice to have a more physical approach and a more stable approach for reflectance retrieval. And I think we can come up with quite a good solution for that as well. So I don't go into those today because it's not yet published and not yet finished, but it's I think it's on the way. There are lots of other corrections methods which are not commercially available, but you can get them directly from the developer. Sometimes you can try them yourselves, and some of them are quite good, quite well done. Maybe I can mention the SEN2COR model. That's a sentinel atmospheric correction, which is often used with people using satellite data. And the same as for the SMAC, that's a simple method for Mary's toolbox. It's also well working for satellite imagery. And for but none of them is, from this list, almost none of them is available for imaging spectroscopy. So you have to be careful. Atmospheric correction for satellites is just a different topic than atmospheric correction of imaging spectroscopy data. And there you maybe the only one which would be available was the ATREM method, but that one is currently not available to the public. So you could get access to it if directly collaborating with the JPL people. So that's about an overview of what we have as corrections. Here's just for the ATCOR variations. You will be working with ATCOR 4 afterwards, the airborne version. The satellite version has the 4 modules for multispectral and hyperspectral data and for flat and rock terrain. So the assumption here is that you got a small field of view. So it's a small field of view. This means within the field of view, we assume only one direction. That's the satellite situation for standard high resolution imagery. You don't have a lot of variation of observation angle within image. That's not nowadays it's no longer very true. So for large sentinel imagery and Landsat imagery, we have to take the direction within image also into account. But most standard like high resolution satellites, this is a good approach. Then you only take the average direction into account. On the other hand, for the airborne imagery, you have a large field of view, which is often between plus minus 30 degrees, can go up to plus minus 30 degrees. So you have to take these field of view variations into account. That's a major difference. And also the flight altitude aircraft is an additional dimension of the lookup table. So for the satellites, it's always above atmosphere, but for the airborne case, of course, the aircraft's altitude varies. And for ATCOR 4, it's starting at about 1,000 meters to 20 kilometers. If you go below 1,000 meters, we get problems with ATCOR 4. That's why we started to develop the other one for drones. You have to reformulate some of the equations to make it work correctly for low altitudes, very low altitudes, very close to the ground. Now, the inputs I mentioned before in the scheme. So we need the image, the lookup table, and the geometry. And sometimes you also take the elevation model in there. Sometimes you could take the meteorological information. That's very seldomly done. Because what we learned is if taking external meteorological information, often you get results are worse as if you derived aerosols, for instance, from the image itself. It's much better self-consistent if you derive it from the image and apply it to the same image than taking it from a different image. And then, of course, there's a lot of configurations and options in the code. So if you try to process 20 satellites or 20 different airborne instruments, each of them has different problems. And that's why if you want to cover with one package all of these sensors, you got to include options and lots of options, and this makes it sometimes difficult to handle for a user. So that's the configuration parameters. The outputs, as mentioned before, bottom of atmosphere reflectance or the spectral albedo. You get side outputs like the water, the parameters, the atmospheric parameters, and illumination on the ground. Also, you can get some standard outputs like internally there are some classifications, some quality checks are done, and so on, which can be written as well for further analysis. So this was about the setup, and now if going into what can you correct for? I focused very much on the radiometry before and on the spectra. But on the other hand, you also have the spatial inhomogeneities. So not the spectral problems, but the spatial problems. These are, for instance, terrain, the illumination influence. And then there are the view angle dependencies and cirrus and haze contaminations. Also, you have always, specifically for satellites. And all the shadows are the major spatial effects you see in the imagery. So these spatial effects, they are visible, whereas the spectral effects are hardly visible. In your last exercise, there was a task, can you see any spatial effects? And you couldn't, I guess, in this small image. Maybe you could if the image was very large and covering a mountain valley, you could see maybe some spatial effects in clear sky. But usually it's very hard to see the spatial effect of atmospheric correction on a small scale, unless you do shadow correction. How to correct for terrain influences. So you have to take these paths from the side into account, from terrain, and you also have to take the sky view factor into account. So how much of the sky you see. Both of that has to be calculated beforehand from a digital elevation model, which DEM, which gives you the sky view factor, or if it gives you the slope and the aspect. So here it's slope and aspect of every pixel. So the direction of the slope, so the orientation of the pixel. This are the influences of the terrain which are taken into account, and if you correct for them, this is on the left hand side without correction. That's the illumination, and then you can apply the illumination. How to apply that's another topic, and there are lots of publications around, and we are still publishing and trying to improve that. So Marius Höckle is working on that at your institute as well, and at the University of Zurich. And there is still room for improvement. So it works in many cases, but as you see here, you get little overcorrections at ridges, and these artifacts can occur in imagery, and you always have to. Or also here you have, if the pixel accuracy is not given with the geometrically, you get strange effects, and you want to have smooth appearance of the outputs. The advantage of this illumination correction is, of course, you get the same brightness on all slopes, so you should get closer to a bihemispherical reflectance through a spectral albedo. Otherwise, the brightness would disturb certain analysis methods. For the cirrus correction, that's for satellites. And you're using a signature at 1.375 microns. That's a fully absorbing band. And there you only see the cirrus. And if you correct for it, you can completely remove these effects. This can also be done in combination with haze. So this is a large scale in Patagonia correction we did. And you can almost completely remove that from the cirrus band together with the haze detection method I was talking about last time. Cloud shadows is a different topic. So in the shadow, we only have diffuse irradiance. So in a shadow area, like here to the left, and this diffuse irradiance can be quantified if you have the aerosols right. And if you once have it right and you know where the shadow is, you can correct for it as it was done in this imagery. Problem is that is detection of the cloud shadows or of the shadows. And the other problem is to have the correct diffuse irradiance spectrally. So this may look nice, but it was more or less an ideal situation. In many cases, it won't work that well. Here's another example for very high resolution data, like photogrammetric data, where we applied the same method. So you can now reduce the shadows also by calculating the diffuse irradiance, but you need to detect the shadows first. And if you see, that's Thun, by the way, train station. But you may also see problems here. For instance, some of the cars are corrected because they are blue and shadow is blue. So blue cars are detected as shadows and they get overcorrected. That's one of the problems we had here. And yeah, you had to adjust the diffuse or the aerosols correctly as well for that. So that's just for spatial effects, and that was number. Now, test some questions regarding those. Side outputs. Yeah, one could say which side outputs are created. Well, side outputs is the illumination, the precipitable water, aerosol optic thickness. Major difference between airborne and spaceborne. Airborne has more. That's flight altitude plus angle. There's one thing more to consider. Airborne is instrument-wise much more complex because every airborne instrument is different. In satellites, we have a standard instrument which is well known. In airborne, it's usually not as well known. And if somebody buys the same instrument again, it will not be the same as the one from the first customer. So if you have various instruments in the air, each of them behaves differently. Is it possible to correct clouds by atmospheric correction, get rid of clouds? Well, you have seen cirrus is working, but other clouds are too thick. You could think in the infrared you can see through clouds, you know that maybe, but that's not done. Spatial effects in mountain areas due to terrain elevation, that's well illumination again, plus a little bit of the dust in the valleys. This which could be visible, the bluish stuff at lower altitudes. So it's the height of the terrain plus the illumination which is applicable. Yeah, that's for repetition. Some words about post-processing. Well, I'm running out of time. There are two post-processing steps which you should remember. The one is the polishing. I already mentioned it earlier today. You just remove noise, and this there are various methods around. The simplest one is just to smooth out the noise. There are dedicated filters for that from signal processing, like the so-called Savitsky-Golay filter. And you can also search for systematic noise, like if you compare to a flat spectrum and if you see the same noise in every pixel, you can remove the systematic variation as well with a flat field approach. So that's a systematic, and non-systematically you need statistical correction. So these are two ways to remove noise. There is in the ATCOR package, there are a few of them implemented, and you can try them in the exercises afterwards. Try to find maybe systematic variations or non-systematic variations as well. In the image you have is maybe not the best suited because it's a very well calibrated instrument. So you don't see that much noise as in other instruments, but you still can try if you can remove some of it or how much is left. And what do we have available? That's the statistical radiometric. Yeah, statistical is just smoothing, filtering. Radiometric is you search for systematic, that's systematic. And Fourier transformation is one which is seldomly done, but which is very hard to do it in an automatic way because you need some interaction to set a limit of the which frequencies to get rid of and so on. So that's why I think we won't work with those now, and I guess you can easily forget about these other two options. So here is an example what you get with a statistical filter from left to right. There's a lot of variations in the water vapor band before correction, and after smoothing, you can get rid of that. And yeah, that statistical filter, I think it was a Savitsky-Golay. So polishing, the only thing you need to know is don't forget about polishing and apply a standard method whenever you see such wriggles and problems, because a typical spectrum here should look like that. So there shouldn't be any variations in a range of 5 or 10 below 10 nanometers. So if you look at laboratory spectra of natural targets, they are always naturally it's smooth to 10 to 20 nanometers. So all natural spectra are in this range smooth. Everything which is seen, which is not smooth in this range. So if you see 1 or 2 nanometer variations in a range, as you see here, this is in the range of 5 nanometers or so, this variation. Then there is a problem with the correction or with the instrument. That's why it's well allowed to smooth out this spectra. That's you get physically the better result, or you're approaching reality much better if you do some smoothing instead of not doing it. So there's always a discussion if you should change your data, or if you destroy your data if you do too much processing on it. But here you improve your data basically. You have to be careful in the sphere shortwave infrared. There it's to about 5 to 10 nanometers. So specifically some geological features are visible in a range of about 10 nanometers. So there you have to be careful not to smooth too much. That's one other thing. I see I'm running out of time, and that's why I won't do anything about BRDF correction now. It's still in here. It will not be part of the exam, the BRDF correction. But if you want to look it up, there is a short description in this presentation here. Just one word, what do? We want to get rid of a cross-track BRDF effect. So if you look to the side, you see a brighter image as seen here. And this brightness difference can be easily about 20%. And if you correct for it, based on the surface, then you can get a result like that. So before correction, after correction, by applying BRDF effect models, and so you get finally the so-called B-hemispherical reflectance, BHR, or spectral albedo. It's just the outcome of the BRDF correction. Everything else can be read in publications and also in the manual.